Okay, let's continue. Now let's consider the how to construct titration curve with a spreadsheet. Okay, see how to reproduce EDTA titration curve by using one equation that applies to entire titration. Yeah, concept is the same as the acid-based titration. Yeah, but I think it's much simpler than that case. At fixed pH equilibria and mass balance equations are sufficient, okay, to solve all unknowns. Okay, so let's consider the metal or ligand. Here is a ligand, maybe EDTA, or any other ligand. Okay, let's consider one-to-one complex. Okay? And here, formation constant is defined as this way, and the metal ligand complex concentration is given by formation constant multiplied by metal, free metal, and free ligand concentrations. Okay? And we apply the mass balance for metal and also for ligand. Okay, for metal, and the total metal concentration, yeah, including free metal ions and metal ligand complex, is given by this one, this equation. And then since we started with initially for the metal ion, initial concentration is C sub m and volume is Vm. So, and this one, the numerator is the moles of total metals, okay? And since we added EDTA solution, the volume changes from Vm to Vm plus Vl. Here Vl is the EDTA, added EDTA volume, and so we do the same thing for the ligand. Okay, from the mass balance, the total ligand concentration is given by L plus ml. Likewise, we write this way. Only the numerator is different. Okay, numerator is the total moles of ligand. Okay, so initially, yeah, the Cl is the ligand concentration and Vl is the ligand volume, and we add Vl. Okay, so as titration goes on, the Vl is only changes. Okay, here. So now we have 1, 2, 3 equations, and now rearrange these equations uh, to obtain. Let me see the equations we will use later. And here, rearranging this one. This is a simple rearrangement. Yeah, rearranging this mass balance equation for M, we get this one. For L, we get this one. And here, from this equation, we write the equation for free ligand concentration. Yeah, it is given by this one, and we substitute this one into this equation here. Yeah, and then we can express only in terms of free metal ion concentration. Okay, although it is looking a little bit complicated. Actually, the derivation is not that difficult. Okay. Okay, here now we define the phi. Okay, phi here, and it is by definition this is a ratio of moles of ligand with respect to the total metal, yeah, moles. Okay, and then uh, using, let me see, this equation here, and then finally, yeah, we get this rather complicated equations. Okay, and then I strongly encourage you to derive to get uh, this equation for phi, right? And now you see uh, the way the to get the entire titration curve is done this way. Instead of you change the ligand volume, but you we fix metal ion concentration and then find out, yeah, the ligand volume, to get that metal ion concentration. Yeah? This way was already done in acid-base titration case. Okay? And here in the column B here, you fix the PM values here. Okay? In this case, it's from 1.398 down up to 8.73. Okay, and then you find to make, yeah, this PM. Now, what's the volume of a ligand? All right, yeah, that's the way how we construct entire titration curve. Okay, like that. Yeah. So let me see. Input is before. Yeah, this is the input. Yeah, P column is the input. Output column is E4 column. Right. This is ligand volumes. Okay, and then later we plot the curve. Yeah. Ligand volume as an x-axis and PM as a y-axis. Okay, right. To find initial P point, Vary PM until VR is close to 0. Okay, anyway, this is how the calculation is done, right? And in this case, use KF prime, yeah, conditional formation constant instead of KF. Okay, assuming we are working at a constant pH. All right. This is a case of calcium titration with standard EDTA solution. All right. Yeah. And here, yeah, this assumed that pH is fixed, in this case at pH 10. Well, next topic is auxiliary complexing agents. Auxiliary. And sometimes, maybe many times, we need another complexing agent when we employ EDTA titration. Why that is? As you saw, the best titration of EDTA is done at quite basic conditions. Okay, because at basic conditions, alpha 4 minus alpha y4 minus value becomes large. Okay, so conditional formation constant is quite large. Yeah? As solution becomes more and more basic. But there is a problem. Okay, at the basic conditions, many metal ions form precipitates. Yeah, by reacting with hydroxide. Okay, for example, um, ferric ion. Okay, ferric ion easily forms ferric hydroxide by reacting with hydroxide. So yeah, that's the big problem. So in a very basic solution, before titration, yeah, the many metal ions forms the metal hydroxide and precipitate, yeah, on the bottom of the flask. Yeah? So that causes problem. So we have to anyway to avoid such a metal hydroxide precipitates. Okay? How do you do that? And the idea is to use another complexing agent called auxiliary complexing agent to first make a complex with metal ions. Yeah? Yeah? Once metal ion, metal ligand complex is formed, yeah, that doesn't precipitate. Okay, so that way we can avoid precipitates. Okay, and then we add standard EDTA solution, and since the formation constant of EDTA is much higher than ordinary this one, the ligand in case, so EDTA now takes the metal ion from metal ligand auxiliary complexing agent, this complex, right? Yeah, and then titration can be done without precipitate. Okay, And these two compounds, for example, tartaric acid and citric acid, they are also good complexing agents. Okay, and citric acid also, yeah, since they have these oxygen atoms, yeah, these oxygen atoms acting as a ligand. Okay, the electron pair donor, yeah, and also the 3-ethanolamine also a good complex agent, but the formation constant of the metal ions with these auxiliary complex agents are not as great as metal EDTA complex. Okay, yeah, that's the idea. Okay, now we can develop the theory in this case. Okay, let's write this way. The metal and the ligand, this ligand here is auxiliary complex agent. Yeah? And then we write equilibrium constant. In this case, let's say instead of K, let's say it's a beta 1. Beta 1 is ml divided by m multiplied by L. Okay, this one, this way. And but now the problem is that this metal ligand complexation, yeah, doesn't stop here. Okay, and it goes on, and then ml also now react with L again. L. Okay, I'm sorry, it is not written here. ml plus L equals ml2, like that. And then we can write the equilibrium constant for that equation, which is beta 2. Okay, yeah. So usually, yeah, the difference between EDTA and auxiliary complex agent is that EDTA all the time makes one-to-one complex, but many other auxiliary complex agents forms a complex not one-to-one, one-to-one, one-to-two, one-to-three, yeah, like that. All right. So we must be careful, okay? And then we have to develop the theory how to deal with the case. Okay? And again, we can define the we can calculate the fraction of a metal ion in the uncomplexed state. Okay, here alpha m is defined by free metal ion concentration divided by Cm. Cm is what? Cm is a total metal concentration. Okay, when let me see, the ligand makes complex. Okay, Ml and Ml2. All right, and then from the mass balance equation, Cm is written in this way. Cm is free metal ion concentration plus metal monoligand complex concentration and metal what's it, diligand concentration. All right, and using beta, beta 1 and beta 2, like that. Yeah, we can rewrite for Cm is given by m and parenthesis 1 plus beta 1 L plus beta 2 multiplied by L squared. Okay. All right. So alpha m, since Cm is given by this one, and alpha m is expressed this way. Alpha m equals, yeah, rearranging is that, and then we get alpha m equals 1 over 1 plus beta 1 and ligand concentration plus beta 2 ligand concentration squared. Okay, here this is alpha m. Again, this alpha m is the fraction of free metal ion. Okay, now things it becomes more and more complicated, but not difficult to understand. Here is an example. Ammonia complexes of zinc ion concentration of free ammonia is 0.1 molar. Okay, ammonia. Yeah? Ammonia is a very good complexing agent. Okay, let's see. The initial concentration of ammonia is 0.1 molar. Wow, this concentration is a rather high concentration, and this ammonia makes these four different types of complex with zinc ion. Okay, zinc monoammonia complex and the diammonia, the triammonia, tetraammonia, right? Yeah. So zinc ammonia complex forms exist in four different forms. Okay, and for each, let me see, for this zinc mono ammonia complex, beta 1 is 10 to 2.18, and for beta 2 is higher than this one because they are, uh, it becomes, greater. Okay, uh, at this point, it is important to different, tell the difference between beta and K. They are all equilibrium constant, but K values, okay, it is called stepwise, okay? Equilibrium constant, and beta is called cumulative equilibrium constant. Okay. Anyway, beta 2 is greater than the beta 1 and the beta 3 and beta 4, like that. Okay. And first thing we have to do is to calculate alpha values for free zinc ion. Okay. It is given by this one, and then we calculate. Now we get 1.8 times 10 to minus 5. Oh, very small. Okay, that means that um, without now in the before you add EDTA concentration, and in the presence of ammonia of this concentration, and free zinc ion concentration is already quite low. Okay, very low, because alpha its fraction is only 10 to minus 5. Okay. Okay, now let's consider the EDTA titration with let me see, this one, EDTA. Yeah. Kf as usual is defined this one, and then here, the alpha 4 minus, instead of alpha 4 minus, we can write this one, substitute alpha and EDTA, and now we instead of this free metal concentration here, we already get, let me see, here, yeah, we use alpha and total ion concentration, and we use this one, okay, because free metal ions concentration is given by this equation. Wow, and the rearranging, yeah, we move this alpha, these two alpha values to the left hand side, and then here we get this new equation, and then it is called effective formation constant. Okay, Kf double prime is given by alpha for zinc ion and alpha for free EDTA, totally deprotonated EDTA fraction, and multiplied by EDTA formation constant Kf. Okay, this is effective formation constant. Okay, this one applies only when the auxiliary complex agent is in the solution. Okay, yeah. Here is a good assumption. Yeah, important assumption. EDTA is much stronger complexing agent than ammonia. Yeah, that's very important, and in most cases it is true, because you look at that, ammonia zinc formation constant is only, beta 4 is 10 to 8.7, but with EDTA, the Kf is much higher than this one. Therefore, all EDTA bind zinc ions until the metal ion is consumed. Right? So you know the idea here. Although the auxiliary complex agent binds the metal ions before EDTA is added, and then when EDTA is added, EDTA now takes all the metal ions from the auxiliary complexing agent. Okay, yeah, that's the idea. Okay, yeah, let's stop here temporarily, and I will continue.